And so now we have the opportunity to go through a couple more problems over the next 45 minutes. So all the problems that I have circled in red are problems that I've already gone over. So you're going to get a video of them from the earlier class. So I did problems 2, 5. I did problem 8A, 13, 14, and then I think problem 15 as well. So there's already a video where I go through those problems that I'll send you. And then you can ask me whatever other questions you have. So before I just start choosing problems, are there any problems specifically people want me to go through from the exam review? I'll start with, I think a good problem to know how to do. Let's focus on, I think the chapter 17 stuff, like you have to know how to do chapter 16 to do chapter 17. So both of them are really important. But there's going to be at least 3 problems on the final from chapter 17. There's probably going to be like 4 or 5, I would say, right? Where you have to do like Green's theorem, Stokes' theorem, and the divergence theorem. So let's focus on problem 18. This one's kind of similar to a problem from last week's group work that I thought was a little bit more difficult. This one isn't as hard as that, but it's the same idea. So for problem 18, it wants you to show that the circulation of F, which is the following vector field, around any curve C on the surface of the cone z squared is equal to x squared plus y squared, ends up being equal to 0 in the figure below. And I shouldn't have told you to use Stokes' theorem. On the exam, I'm not going to give you such a hint. You have to figure it out on your own. But I mean, why do we know that we should be using Stokes' theorem? Well, we're looking at this curve C here, and it's asking us to find the circulation. So when I'm asking you to find the circulation, what this means is I'm asking you to find the following integral. So the circulation is really the vector field integral, or not vector field, vector line integral over C. But the issue is we don't really know how to parameterize C at all. So it'd be difficult to compute this integral because we don't know what R of t is going to be. And so we kind of have to hope that in applying Stokes' theorem, things are going to cancel out and things are going to end up equal to 0, which of course is what ends up happening. If that didn't happen, you would have to have more information to determine like how would you actually find this integral. Right. So as a reminder, what Stokes' theorem allows you to do is instead of integrating over the curve C, you can instead integrate as a double integral over the interior of C. So we want to consider the following double integral. Right, we want to do the double integral over S of the following. So this is going to be the curl of F dot ds. And so we're just going to compute the curl, right? So it's the first thing we do. So I'm just going to write out the vector field so that way I don't have to scroll up and down over and over again. So this is x squared, y squared, and then z times x squared plus y squared. So if you compute the curl of F, so that's going to be of interest to us if we want to use Stokes' theorem. So the curl of F, as a reminder, is the following determinant. Right, so you do the partial with respect to x, partial with respect to y, and then partial with respect to z. And then this is going to be x squared, y squared, and then z times x squared plus y squared. All right, and so if you do these partial derivatives, you'll get a new vector, or really a new vector field. So the first component here is going to be the partial with respect to y of z times x squared plus y squared. So it's going to be 2yz in the first component. And then the second component, I mean, you know how to do this already. So this is like -1 times what we have here. So it's going to be minus 2xz. And then the final component is just going to be 0 because it's this partial, which is 0, minus this partial, which is equal to 0. Right. So this is what the curl of F is going to end up being. And then for the next part, like if we're going to be integrating over S, like we're really integrating over this subregion of the cylinder, or not cylinder, of kind of like this cone that we have. Right, so we could parameterize, like we know how to parameterize the larger cone in general. And then from there, we need to restrict our focus to exactly this patch of the cone, which, I mean, we don't really know exactly what that would look like. So we're hoping that in doing the parameterization, if we do like the composition and then dot with the normal vector, things will work out well for us. All right, so let's focus on the parameterization of the cone that we have, and then we're going to move forward. So the parameterization of the cone is the following. So you should be thinking of a cone as really just being a circle where the higher you go, the larger the radius is going to be. So the z component and the radius are going to be equal. So how you can parameterize this is the following. So we have g. We're going to use the variables theta and z. So the parameterization is going to be z cosine theta, z sine theta. And then it's going to be equal to just z as the final component. And then to find the normal vector, what we do is we take the partial derivatives of both with respect to both variables. So we're going to have like a t theta. Let's do 2z first. So t sub z, this is going to be equal to cosine theta, sine theta, and then 1. The second component is going to be t theta. So this is going to be minus c sine theta, and you have z cosine theta, and then you just have 1. Oh wait, no, you have 0. Lost my train of thought. Yeah. So this is what the two tangent vectors are going to end up being equal to here. Then find the normal vector. You take the cross product of both of these vectors. So we have n is equal to the cross product of t sub theta with t sub z. And I mean, we already computed one cross product, so I'm just going to write out what this ends up being equal to. So this ends up being z cosine theta. This ends up being z sine theta in the second component. And then the last component ends up being minus c. And so what we end up doing here now is when we're doing this integral, right? Like we have that the integral over the curl of f of s ds. This is really equal to the following double integral, right? You do the composition of the curl of f with our parameterization g, and then you dot with the normal vector. And then you have d theta dz. So let's just see what ends up happening. I mean, I kind of spoil it. Like this dot product should end up being equal to 0 because I say like the circulation should end up being equal to 0. But let's actually prove this now. Right, so if we do the curl of f composed with g, let's go up here. What this means is the first component, kind of have to zoom out a little bit more. The first component of f means that you're squaring whatever the first component of g is going to be. So you'll have a z squared cosine squared theta for the first component. So this is going to be equal. Yeah, so this is going to be, yeah, x, wait, let me make sure. Yeah, x squared, first component. So z squared cosine squared in the first component. The second component is going to be y squared. So you're going to have a z squared sine squared. Theta. Oh, I'm not looking at the right thing. I knew something was off. I was looking at the f and not the curl of f, right? The curl of f, there should be 2. Sorry, I was looking at the wrong vector field. So we should be doing the composition of the curl with g, right? So it's going to be 2 times y. So it's going to be z sine, and then you multiply by z. So it's going to be 2 z squared sine theta in the first component. The second component is minus 2 times x times z. So it's going to be z squared times z. So it's going to be a minus 2 z squared cosine theta. And then the final component of the curl is always 0. So if you do the composition, it's going to be 0. And then you dot with the normal vector. So we found that the normal vector, I'm going to need a little bit more space. The normal vector, this is going to be z cosine theta, z sine theta, and then minus c. And then this is like dz d theta, or whatever order you want to do it in. Yeah, so now if you do this multiplication, like this dot product, you'll have 2 z cubed This is going to be the double integral of 2z cubed, and they have sine theta, cosine theta. And then that's going to be minus 2z cubed. And then you get sine theta times cosine theta again. So this will be sine theta, cosine theta. And then obviously these two things, they're equal to one another, so they cancel out. So these two terms cancel out with one another. This ends up just being equal to 0, which is what we wanted, right? In the beginning, it was asking you to show that the circulation ends up being equal to 0, regardless of the closed curve C you're looking at, and that's exactly what we ended up finding, right? So I messed up a little bit by considering F instead of the curl, but yeah, this is what it ends up being equal to. And so I think this is a harder problem, and that you kind of have to go through like Stokes' theorem, then you have to actually go through with the parameterization and show the dot product ends up being equal to 0. Any questions about problem 18? Yeah, so again, I think this is a harder kind of problem. It's a little bit different from what we've been doing before, but it's still very doable. Yeah. Any other questions people want me to go through before I just choose some? Let's see, maybe we can look at, I feel like we should look at let's do problem 9. So problem 9, there's kind of like, it's kind of guaranteed there'll be a problem similar to this on the exam. I mean, it'll be a little bit different, but the idea will be the same. Right, so it wants you to compute the following vector line integral. So we're doing the vector line integral over the vector field F, or of the vector field F over C. So that means it's like a vector line integral. And I mean, it's nice in that it tells you in the beginning that F is equal to the gradient of some scalar function F. So this means that big F is a conservative vector field. So we can use the fundamental theorem of conservative vector fields here. And then we're given some more information, right? It tells you that the scalar function F is given by 4x squared times the natural log of 1 plus y to the 4th plus z squared. And then we're also given the path R, right? So the curve C is parameterized by this R of t, where the first component is t cubed and the natural log of 1 plus t squared, and then e to the t, where t ranges from 0 to 1. Right, so the first thing we should do is we should check and see if C is going to be a closed curve or not. If C is a closed curve, then this means that the integral is going to end up being equal to 0. And so what we're going to do is we're just going to plug in R is equal, or R of 0 into this, and then R of 1 into this to see where the endpoints are going to be. If the endpoints are equal, that means it's a closed curve. Otherwise, I mean, we'll just have to do a little bit more work to determine what the vector line integral is going to be. So if we plug in t is equal to 0 here, you get 0 squared, or 0 cubed, plus the natural log of 1 plus e to the 0. So that gives you the point 0, 0, 1. And then if you plug in t is equal to 1 into the parameterization, you get 1 cubed, which is 1. You get the natural log of 1 plus 1, so that's the natural log of 2. And then the final component, you plug in t is equal to 1 for e to the t power, so that'll give you an e. So you can see this isn't a closed curve, right? Because this point is different from this point, but we can still make use of this information when computing what this vector line integral is going to be. Right, and so we can still use the fundamental theorem for conservative vector fields. I'm going to try and squeeze it in here. It's not a good idea, but I'm going to do it anyways. So we want to find this integral. And so the fundamental theorem for conservative vector fields tells us that this integral is going to be equal to f evaluated at the right endpoint, or the largest point. So f of R1 minus f of R0. Yeah, this was a bad idea. I don't have like any space. Yeah, so we know that the difference is going to be like this vector line integral is going to be the difference of these two. We already found that f of R1 is equal to this point. So it's really asking you to do f of 1 natural log of 2 e. And then this is going to be subtracted by f of 0, 0, 1. right? So this is what the fundamental theorem for conservative vector fields tell you. And so it gives you what f of x, y, z is. So it's just a matter of plugging this point into here. So we'll have 4 times 1 times the natural log of 1 plus the natural log of 2 to the 4th power plus e squared. And then if you plug in 0, 0, 1, I mean, it's just going to be equal to 0, right? So this ends up just being equal. Maybe this is I should have made more space, but whatever. So this is going to be 4 times the natural log of 1 plus the natural log of 2 to the 4th power plus e squared. And then this part ends up being equal to 0. So if you plug in 0, 0, 1, it just ends up being equal to 0. So this is all you're left with, is this point right here. That's the solution to problem 9, right? So hopefully, I mean, it's just a matter of recognizing like that you should be using the fundamental theorem for conservative vector fields. Once you know that's what you should be using, the problems usually aren't going to be that bad. Any questions about problem 9? Yeah, and then there's another problem where you have to make use of the conservative vector field theorem, but I did it in the previous class. So if you look at problem 5, like immediately when you see f is equal to the gradient of some function, you should immediately think like I can use the fundamental theorem. And so this problem is pretty similar to what we just did, except part B is a closed curve, so it ends up being equal to 0. Okay, what next? What other problem should I try to choose one? Let's see. Maybe we should do, I think this kind of problem could show up. Something like problem 12 could show up on the final. I mean, you have to know how to compute the curl and the divergence of something, right? In order to do Stokes' theorem and the divergence theorem. But I could also ask you to kind of think more generally about what the curl and the divergence or like these kinds of compositions end up looking like. So I kind of like these sorts of problems. So let's go through problem 12. We've seen problems similar to this on the group works. So let's formally explain this one. So this is problem 12. So there's 4 parts to problem 12. So part A, it's asking you whether or not the following equation is true or false. So we have the curl of the gradient of f. It wants you to show if this ends up being equal to the 0 vector. For part B, it's asking you about the divergence of the gradient of f. It wants you to determine if this ends up being equal to 0. C, we're looking at the divergence of the curl of f, and it wants you to determine whether or not it's going to be 0. And then lastly, for part D, it's asking you to find the gradient of the divergence of f, and it wants you to determine whether or not this is going to be equal to the 0 vector. So some of these we've already seen before, right? So like problem 12, I'm not going to go into, or 12a, I'm not going to go into full detail about. But this goes back into, I think, section 16.3, right? It's asking you to find the curl of the gradient of a function. What we've seen in the past is that if you have a conservative vector field and you compute the curl of that vector field, it ends up being equal to 0. If you're looking at the gradient of a function, that's always going to be a conservative vector field, right? Like by its definition, it's going to be a conservative vector field. So for part A, so the solutions I'll write in green. So for part A, we have that the gradient of f is a conservative vector field. Again, by the definition of a conservative vector field. And so what this means is that the curl of the gradient of f is equal to 0. So this is something we looked at. Let me see if I can find the notes. In case you don't remember this, we talked about this a little bit when we did section 16.3. I think this is, let's see if I can find it. Oh yeah, it was, maybe it's the next page or the page after. Oh yeah, it was this page right here, right? So like if F is a vector field on a simply closed domain, then if the curl of F is equal to 0, this happens if and only if like F ends up being conservative. And the big idea is, but if you do like the curl of the gradient of a function, it's really just going to give you like a difference of mixed partial derivatives where you have like f of xy is equal to f of yx or something like that. So that's why it always ends up being equal to 0. So that's something we've seen already. The other ones I think we've seen on group works or on other problems. So let me see. Oh yeah, this next one was actually a problem on last week's group work on Friday. So for part B, it's asking you to find the divergence of the gradient of f. So if you do the gradient of f, like the divergence of the gradient of f looks something like this, right? So let's first write out what the gradient of f looks like. The gradient of f is going to give you a vector. It's going to be the partial of f with respect to x in the first component, the partial of f with respect to y in the second component, and then the partial of f with respect to z in the third component. If you compute the divergence, what this means is you're going to be taking the partial derivative of f with respect to x again, and then you add to that the partial derivative of f with respect to y again, plus the partial of f with respect to z again. So if you compute the divergence, this is going to be the second order partial of f with respect to x, plus the second order partial derivative of f with respect to y, plus the second order partial derivative of f with respect to z. And then I think on the group work, we said this was also equal to the Laplacian. So it's like equal to like the gradient or like the Laplacian of f. You prove that. So the question is like, is this always going to end up being equal to 0? Does anyone know? Like, does this end up being equal to 0 always or no? Yeah, go ahead. No. Yeah, it's not always going to be equal to 0. And you can choose some like pretty basic like examples. So for instance, if we had like f of xyz is equal to like 2x squared or something like this. If you take the second order partial derivative of f with respect to x squared, like this is still going to be non-zero. This will just be equal to 4. So if you did like the divergence of the gradient of f, this is just going to be equal to 4, which is not equal to 0. So this always isn't equal to 0, isn't always equal to 0. Okay, yeah, so that's part B. Any questions about part B? Yeah.
Is that like last C?
Oh yeah, it should be there should be a square here. I'm kind of regretting choosing this problem to go through because now there's still 2 more parts to it. So this is another group work problem. I think part C we've done a group work on before. I think it was group work 11. For this one, it wants you to determine if the divergence of the curl of f ends up being equal to 0. So you just go through it formally, right? So if you want to go through this, we can write out, say like f is equal to the following. So this is like f1, f2, f3. And so the curl of f looks like the following. So if you write it out in a general way, this is equal to the following determinant. So we have I, j, and k. This is like the partial with respect to x, partial with respect to y, partial with respect to z. And then this is f1, f2, f3. So I don't want to use the Leibniz notation. I'm just going to write it in the following way. So it's going to end up being the following vector, right? So do the partial of f3 with respect to y. So this is like partial of f3 with respect to y, minus the partial of f2 with respect to z. That's the first component. The second component is going to be minus 1 multiplied by the partial derivative of f3 with respect to x, minus the partial derivative of f1 with respect to z. So it's really f1 with respect to z, minus f3 with respect to x. And then the last component is the partial of f2 with respect to x, minus the partial of f1 with respect to y. So this is the general form that we have with respect to the curl of a vector field f in 3 dimensions. And then from here, what we want to do is we want to compute the divergence of this thing, right? So if we're doing the divergence of the curl, I'm going to be lazy and just write it out like this. So I'm going to add in, we're doing the divergence of this thing. which means we're really taking the divergence of the following vector. And so if you perform the divergence, what you're doing is you're taking the partial with respect to x of this, plus the partial with respect to y of this, plus the partial with respect to z of this. So this is going to be equal to f3 yx minus f2 zx. So it's kind of messy, right? Like there's a lot of notation, but if you follow along and you're consistent, things work out. So this is f1 with respect to z and then with respect to y, f3 with respect to x and then with respect to y, and then this is going to be plus the partial of f2 with respect to x and then z minus the partial of f1 with respect to y and then z. And then if you do everything correctly, things should end up canceling out with one another, right? So you have f3 with respect to y and x, and then you have minus f3 with respect to x and y. Doesn't matter the order, they cancel out with one another. You have minus f2zx plus f2xz. Again, it doesn't matter the order, they're equal to one another. And then you have f1zy and then f1yz. So those things cancel out. Everything cancels out, it ends up being equal to 0. So you always have that the divergence of the curl is going to be equal to 0. Okay, and then for part D, I'm just gonna tell you that it ends up not being equal to 0 because I'm tired of doing this problem. So I'll post the solutions later. I'm just gonna say like this is something you can explore on your own. This is not always equal to 0 for part D. Oops. Yeah, so I could ask you to maybe do like one of these 4 smaller problems. I'm not gonna give you like a list of like 4 or 5 and be like verify all of them. There could just be like a problem like this, like only that one, or it can only be like part D or something like that. Yeah, question.
In the exam, for like part C, is it something that you would want us to work out, or would we be able to say that like the 2 functions just naturally cancel one another out?
You would have to show it, like you would have to go through the process. I mean, I'm probably gonna ask you to do something different from this one, so you're expected to show that you actually see how things work out and why things cancel out to 0. Any other questions? Yeah, so that's the gist of it for whatever problem this is, problem 12. I mean, part 12, I think part D is pretty much the same as the others. You just have to follow the definitions and then see what ends up happening pretty much. Okay. I should probably do a vector. We should probably do like a Green's theorem problem. Before I choose a problem, does anyone want me to go through one specifically? Yeah, so we should go through a Green's theorem problem. I don't think I've explained a Green's theorem 1 in my previous class. I'm gonna erase this part. Again, I'll post the solutions after class today. Which one's better? Let's go through problem 11. So for problem 11, it wants you to evaluate the line integral, where the first component of our vector field is given by 3x plus 5y minus cosine of y. And then the second component is given by x times sine of y. And then it doesn't tell us much about C, aside from the fact that C is any closed curve and that encloses a region with an area of 4. And then it tells you that it's oriented counterclockwise. If it were oriented clockwise, that means you'll follow the same process, except you'll just multiply by -1 at the end. Okay, so this is problem 11. Let me make a new page. Oops. So I'm just gonna record the important information before I start writing it down. That way I don't have to scroll up and down over and over again. Okay, yeah, so this is the vector field that's given to us is F. So this is going to be 3x plus 5y minus cosine y. And then the second component is x sine y. Yeah, and so what it wants us to do is it wants us to find the following integral, right? It wants us to do the vector line integral over the curve C of f dot dr. And again, we don't really know anything about C. So if you wanted to like compute this integral directly, what you'll need to do is come up with a parameterization for C. And again, we don't know anything about C. So this would be I mean, it'd be impossible. Like, we don't know anything about C aside from how much area it encloses. So instead of doing the vector line integral, we want to use Green's theorem to instead do the double integral instead. That's one way of thinking about it. You should also be thinking, right, like it wants us to find, like, we're using the area to determine what the integral is going to end up being. So that probably means we need to introduce a double integral, which is done via Green's theorem, right? Because we only have two components, so an R2. Right, so Green's theorem tells you the following. So now this is going to be equal to the double integral over some domain D. And so what you do with Green's theorem is it's going to be the partial derivative of the second component with respect to x. So it's going to be the partial derivative of x sine y with respect to x. And then this is going to be subtracted by the partial derivative of the first component with respect to y. And then this is dx dy. Not that it's going to matter. Again, we don't know anything about like the bounds for x and y. So we kind of have to hope that things cancel out or we get something else that's nice. So this is going to be equal to the following double integral. So it's the double integral over d. So the derivative with respect to x will just give you a sine y. And then this is going to be minus the partial derivative with respect to y here. So the 3x is going to go away. You're going to have a minus 5. And then the partial derivative of minus cosine is going to be plus sine y. And so, I mean, things kind of have to work out this way for you to do this problem. What's nice is that all the variables or anything involving a variable ends up canceling out. So the sine y and the plus sine y ends up canceling out. So you're just going to have the the double integral of minus 5. So this is equal to minus 5. Let me write it out like this. This is minus 1 times the double integral over d of 5 dx dy. And then the main observation, we've seen problems like this in the past, where the big idea is you just take this 5 and you bring it outside of the integral, and that gives you a way of thinking in terms of area. So this is really minus 5 times this double integral over d of 1 dx dy. Or let me, instead of dx dy, let's just say it as like dA. Just really drive home the fact that we're relating to the area. So this is really equal to minus 5 multiplied by the area of D. So this is where the area that they tell you in the beginning of the problem comes into play, right? Like it tells you we're enclosing a region with area 4. So we just substitute in this area is equal to 4. So this is going to be minus 5 times 4, which is equal to minus 20. Okay, so this is kind of a classic Green's theorem problem, I guess. Again, it mentions area, and we only have a single integral, so we want to use Green's theorem, so that way we can incorporate the double integral as one way of thinking about things. Any questions about 11? Okay, and then there's another problem on the exam, not on the exam, but on the exam review. That's pretty much the exact same idea. Right, like problem 15, we've done examples similar to this in class where it gives you a double integral and it wants you to relate it to volume. So you use the divergence theorem. So that way you can go from a double integral to a triple integral. So problem 15 and problem 11 are pretty similar to one another, just in different dimensions pretty much. So you should expect to see a problem like problem 15 or a problem like problem 11 on the final. I'm going to ask one of those kinds of problems where you have to relate volume or area with one of these like big theorems. Okay, I probably have time to go through maybe 1 or 2 more problems. I'm gonna ask anyways. Does anyone have like a problem you want to ask before I just choose some? Yeah, go ahead. Which one? 14. Oh yeah, I did 14 in the previous class, but I feel like it's still worth going through. Yeah, so for 14, it wants you to do the following integral. This one looks worse than it actually is, I would say. So we have the following vector field given by z squared, x plus z, and then y squared in the last component. And then the surface we're integrating over is described by this equation. So it's x squared over 4 plus y squared plus z squared is equal to 1. And so the key word here to understand what this is telling you, I mean, it kind of looks like a circle, but it's a little bit off. This is like an ellipsoid. So you should be thinking it's an ellipse, except it's in 3 dimensions. So you can write it out in the following way. It's really like x over 2 squared plus y over 1 squared plus z over 1 squared is equal to 1. So this tells you that, like, if you ignore this component, it tells you on the xy plane, we have an ellipse where the x radius is 2 and the y radius is equal to 1. So that's how to think about this equation. And then it wants you to, it tells you about, like, it's oriented by outward pointing normals. And it wants you to compute the double integral of the curl of f. This is kind of a red herring, or I don't know if red herring is the right way. I mean, this is pretty much telling you that Stokes' theorem is going to be relevant, right? Like, we're looking at a double integral over the surface of the curl of something. Like, we're probably going to use Stokes' theorem to make it so we do a single integral instead of the double integral. So before I do anything, let's draw a picture. Actually, I'm going to rewrite this again so I don't have to scroll up and down over and over again. So this is z squared, x plus z, and then this is y squared. So let's draw a picture of what we're actually integrating over. So this is going to be the ellipsoid. So this is x-axis, y-axis, and then the z-axis, right? So again, if you ignore the z component, it's going to be the equation of an ellipse of x radius 2. So we're going to have that this is 2, and then we'll have a minus 2 back here as well. And then we're going to have y is equal to 1 and y is equal to minus 1. Right, so on the xy plane, we get something that looks like this. And then we have z is equal to 1. So if you incorporate the z over 1 squared is equal to 1, this is just saying z has a height of 1 here. Right, and we're only considering the upper half of the ellipsoid, so we don't have z is equal to minus 1. We ended up getting something that looks like this. It's not the best picture of all time, but it's better than my previous class. So this is like the ellipsoid. It's really just an ellipse. It's kind of like an upper half sphere, except the base is an oval instead of a circle, right? That's all that it's getting at. And so what this means is we can either compute the curl of f and then do the integral over this surface. What you would prefer to do instead is you want to use Stokes' theorem, so that way you can just integrate over the base, or like the boundary, which is just going to be over the ellipse. Because we know how to parameterize an ellipse. It's just a circle. So it's going to be like 2 cosine of t and then sine of t in the second component. So if you know how to parameterize a curve, it's better to work over the curve than it is to work over the surface, assuming you don't have to do too many of them, right? You would rather do 1 surface integral than like 5 vector line integrals, right? So we're going to use Stokes' theorem. Stokes' theorem tells you the following. So we can do the integral, the double integral over s of the curl of f dot ds. Instead, it's much easier to instead do the vector line integral over f dotted with dr, where this is going to be the boundary of s. Or again, the boundary of s is just going to be the ellipse given by x over 2 squared plus y over 1 squared is equal to 1. And so as a reminder, I'm going to move this down actually. This will kind of be like the last line that we have. So as a reminder, this vector line integral is really just the same thing as the following. So this is going to end up being the integral, spoilers on like the parameter, I guess, from 0 to 2 pi of f of rt dotted with r prime of t et. So we just need to find what this parameterization is. Then we compute the derivative and then we do the dot product. So as I said before, like r of t, you should just be thinking in terms of like, how do I parameterize a circle, except now the radius are going to be a little different. So as we have an x radius given by 2, the first component is 2 cosine of t. And then the y radius is 1, so the second component is just going to be sine of t. And then z, like we're on the xy plane, so z is always just equal to 0. And then t ranges, like we have this full rotation about the z-axis, so we're going from t is equal to 0 to t is equal to 2 pi. So that's where the 0 to 2 pi came into play. And so we care about the derivative of r of t, so we have r prime of t. This is equal to minus 2 sine of t, and then cosine of t, 0. And then let's just compute the composition now. So this is f of r of t. So this is really f of 2 cosine of t sine of t 0. Right, so this is going to be, so f, what you do, like the first component is going to be z squared. Right, so that's just going to give you 0 for the first component. So this is going to be equal to 0. The second component is x plus z, where x is 2 cosine of t and z is equal to 0. So this is going to be 2 cosine of t. And then the third component is y squared. Right, so the third component is y squared, so that's going to be sine squared of t. So all that's left now is you just take this vector and then you dot it with r prime of t. And you can see we're going to have 0 times minus 2 times sine plus 0 times sine squared. So all that's going to be left, all that's going to remain is 2 cosine of t times cosine of t. So this is going to be equal to 0 to 2 pi of 2 cosine squared of t dt. And then from here, I mean, you could use, I'm not going to ask you to do the reduction formula or anything like that on the exam. This ends up being equal. So if you do the integral of cosine squared, it's 1/2 of sine t times cosine t plus 1/2 of t. I'll just tell you this ends up being equal to 2 pi. If you get a problem similar to this on the exam, I might just ask you to like write out what the integral is going to look like with respect to t. So you would have to like get this far, and then you don't have to actually compute what the integral ends up being. But the final answer should end up being equal to 2 pi right here. Right, so this is a more involved Stokes theorem problem in that you have to actually go through and compute the integral. Things don't just cancel out immediately, but it's still pretty doable. Any questions about 14? Okay, so I'll post the solutions to this within like the next hour, and then I'll also post both video lectures and put it on the exam review. Remember to do the course evaluations, and I also have office hours for like the next 2 hours. So if you have any questions, you can find me in my office as well.